explicitly or recursively, in either event, you're going to need the initial value, the A1. All right, but the model that we use for the explicit approach would be A sub n is equal to A1 plus D times n minus 1. All right. The recursive, that's going to accomplish the same thing, but it's structured a little bit differently. All right. So we need the A1 there. We need the relationship between any term in the sequence A sub n and any term that came before that value in the sequence. And then we need some statement of the domain. All right. But that domain is almost always and will always be, for our purposes, n greater than or equal to 2. The domain for the explicit function, if we're talking about the entire sequence, would be n greater than or equal to 1. So this structure applies for any kind of problem that you can be given. So I'm just going to do a quick copy paste and put it right on over here because we're going to need it again in a minute. All right. So A sub 1 is the initial value. That's the first value in the sequence. So we have a negative 2. D, that represents the common difference from term to term. So I'm going to just see how much I have to go to get from one term to the next repeatedly. Make sure I want to make sure that they're the same value over and over again. And if it is, then I know I'm dealing with an arithmetic sequence, and I'll have what I need. All right. So if you're not sure, take two consecutive values and subtract the first value from the second. All right. So in this case, you could actually take the first value and subtract it from the second. So negative 7 minus negative 2. All right. So we're adding a negative 5 to each term. All right. So if I start off with a negative 2 and add to that a negative 5, I'll get the second term in the sequence, third term, fourth term. All right. So it checks out. So my common difference, actually I want to just put this over here. My common difference is a negative 5. So plus a negative 5, or you could just write minus 5. All right. So let me get rid of that and put minus 5 times n minus 1, where n is greater than or equal to 1. All right. So you really only need, for the explicit model, you really only need those two pieces of information, the initial value and the common difference. Everything else just goes into your formula. All right. You can do a quick check on this, whether you want to do it numerically, on paper, or if you want to do it in the calculator. It's pretty easy either way. But let's say you want to do it in the calculator. You just take this expression, a sub n, you can treat that as your y equals, or the y1 equals. But the expression, negative 2 minus 5, instead of n minus 1, you use x minus 1. Go to the table and start with the x value of 1 and any value bigger than that, and see if this sequence comes up. So second graph, starting off at 1, you see I have a negative 2, then a negative 7, negative 12, negative 17. And the good thing about doing this is if they ask me for the 57th value in the sequence, I can go right on down my list to the 57th value, and I'll know what that value is supposed to be. So if a follow-up question said, what's the 57th value in this sequence, I have it. It's negative 282. All right? So it's kind of nifty in that regard. But in terms of the recursive model, it's actually even easier because, again, you still only need the two basic ingredients, the initial value and the common difference. We already have the initial value accounted for. the common difference gets tacked on right here, so minus 5. Again, what this is saying is you have two values within the sequence, a sub n minus 1 and a sub n. Right? A sub n minus 1 is 1 unit before the nth value. So what this is saying is if you want to get from one term to the next, all you'd have to do is subtract 5. I'll actually just show you really quickly. If you were to have a sequence, so this is any sequence, whether it's arithmetic or geometric, which we're going to get to in a little bit. Any sequence would be in this form. You'd have the n values, the first, the second, the third, the fourth, the fifth, and so on. And then the a sub n values. Those are the actual numbers that occupy those positions. So if the n values are the position within the sequence, the a sub n values are the actual numbers occupying those positions. So you'd have a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, dot, dot, dot. But dot, dot, dot could continue on for 100 units. It could continue on for 1,000 units. It could continue on for n units, right? So some large number of values that we just don't know, we're not privy to, right? So if we make that assumption that there's an nth term down the line here, then there must necessarily be a value at that location. What we're saying here when we say a sub n minus 1 is we're saying the term before that. All right, if I say n minus 1, I'm saying that there is a term before the nth term. All right, so this is one term before n. I cannot make my squiggly bracket here, but this one. All right, one term before n. So that would be a sub n minus 1. Then you could also have n plus 1, which would have, so n plus 1 is your location. The term occupying that position would be a sub n plus 1. That would be one term after n. All right, so what we're doing when we write a recursive model is we're just determining or stating the relationship between these two. I want to know what the relationship is between the term that comes before the nth term and the nth term itself. So if I'm telling you that we're going d units every step of the way, plus d plus d plus d, and you could do that for all those finite values, then it would make sense that the relationship would be that you would take a sub n plus 1, add d to it, and that would give you a sub n. So that's where that whole relationship is coming from. All right, in this case, d happened to be a negative number, so we subtracted, but that, it's the same theory. All right. The only difference between what we're doing here and the geometric sequence is that instead of adding, we're going to be multiplying. But it's the same theory. All right. So when you're writing your explicit model, again, we still need the first value, -2. And we need the common difference because everything else is going to be pretty much status quo. All right, so I'm going to take two consecutive values and subtract them. It's actually easiest if we take these two consecutive values. 2.5 minus 1 is 1.5. So I have my common difference, so plus 1.5. Everything else structurally remains the same. All right, so I know my common difference is 1.5. And so that's really it. Right. Anytime you could call on a previous result to determine a new outcome, that's actually a good thing because it means that you don't always have to go back to square one in order to determine a value. All right? So you determine a number's value not by how it compares to 0, but by how it compares to the number that came before it, which could actually be 0 sometimes, but that's the idea. And this has lots of applications. The recursive models has lots of applications in computer programming. So that's one of the reasons why we do this, and open that doorway. But the geometric sequence, consecutive values have a common ratio. All right, so that means that you could multiply any value in the sequence by the same number and you'll get the next term of the sequence. All right, sometimes that number is positive, sometimes that number is negative. But in this sequence, it's pretty easy to see that we're multiplying by 3. For the first one, definitely. We just need to make sure that that's the case for the remaining ones. So times 3, times 3. Then I'd say, okay, well, what do I get if I multiply this one by 3? So it's 162, I think. Quick double check. All right. Mental math. All right. So this has the basis in exponential functions. All right, we talk about growth and decay models. Now, we wouldn't actually use there is a world where we could use it, but in this context, it doesn't really make things very simple if we use the exponential growth formula to come up with the rule. So I just kind of gave it to you, but the idea is, I think I mentioned this when we were talking about exponentials, is that if I'm doubling my height, I'm taking one of me and putting that one me on top of the one me that already exists. So now I have two me's vertically. So I have double my height, but I've only increased by my height by one me. All right. So the rate of growth when you're tripling something, which is happening here, would be 200%. It's always one less than whatever it is that you're increasing by. So the exponential growth model, could be a little confusing when we apply it here. So we just kind of jump right to a rule. And you could see it down here. But aside from the things that are familiar, you have the a sub n, the a sub 1. A sub n is what we're looking for. A sub 1 is the initial value. We have an r there. N is the independent variable, so we're going to leave an n in our final answer and leave it so that we can make substitutions later on. But that r needs to be taken care of. All right? That r is the common ratio. All right? The common ratio is the value that we're using to get from one term to the next. So the way we determine that is by dividing consecutive values. I'm not getting that.
Can I get it?
Sure. So negative.
7201.
Oh, that's main office.
Hello? 14. Office.
Thank you. So take any two consecutive values and divide them. That'll be your common ratio. Except the order matters here. All right? So the term later in the sequence gets divided by the term earlier in the sequence. All right? So when I take these two numbers, when I divide, I'm dividing the negative 20 by the 4 in order to determine what 4 has to be multiplied by in order to get to the negative 20. All right? So through division, we get multiplication. All right, so this gives me a negative 5 as a result. All right, so by dividing negative 20 by 4, it tells me that 4 needs to be multiplied by negative 5 to get to a 20. Then I would just verify that that would hold true for the next term. Negative 20 times negative 5 will give you a 100. 100 times negative 5, negative 500. Negative 500 times negative 5 is 2,500. All right, and so what we have here is what's known as an alternating sequence. Alt, poor quality T. Alternating sequence because R is negative. You know, I mentioned this just to prepare you for the idea that, you know, they give you a multiple choice question that involves a sequence and it has alternating values in terms of signs. So positive, negative, and so on, or the other way around, negative, positive, negative, positive. And then they say which of the following could be the R value. It's a nice, quick way of getting the answer by saying, well, I'll just look for the one that's negative, right? Because that's the only way it would alternate, right? So same idea for number 2. I'm going to take that 8 and divide it by 16. Same idea, going backwards to go forwards. So 8 divided by 16 is 1/2. That's my common ratio. So I'm multiplying by 1/2 every step of the way. 4 times 1/2 is 2. 2 times 1/2 is 1. All right. I'm making something that for many people is very intuitive into something that is procedural. All right. That's to prepare you for the complicated cases. Right? Because I think it's pretty easy to see, like without any instruction whatsoever, if I told you, here's 3 numbers, 16, 8, and 4, give me the next 2, you're going to say 2 and 1. It's not going to take too long before you figure that out. But then when I give you something like 0.8, 0.64, and so on, it's like, oh crap, what do I do there? You know? So we make the process out of the intuition. The explicit formula, a sub 1 represents the first term of the sequence. R is the common ratio between consecutive terms. And N is any term in the sequence, the position of any term in the sequence. I go back and forth between calling it a position and a location. It really means the same thing. I figured I would specify that. Little typo for somebody. The rule should have the domain n greater than or equal to 1. Because it always needs to. So when I'm writing the explicit formula, I really only need the 2 pieces of information, the initial value and the common ratio. So the number that takes me from one term to the next. And that whole division process, I only show that in the event that you can't just pick it off the sequence just by looking at it. Like in the first one, I think it's pretty easy to see that you're multiplying by 2. All right. The second one, okay, you're multiplying by 2, but they go from being negative to positive to negative to positive, so maybe you get a little jammed up on that. So maybe that's where you do the extra work, where you say R is equal to 22 divided by negative 11. And then test to make sure that that works every time. All right, you don't have to show that test. You just gotta, like, I recommend that you do that test. All right, when you get into fractions, decimals, and stuff like that, then, you know, you might be more inclined to actually justify by showing the R computation. But we know the initial value, Actually, in each case, we know the initial value. So a sub n is equal to 5. Right? This time we're multiplying because it's a common ratio. So 5 times 2 to the n minus 1, where n is greater than or equal to 1. A sub n is equal to negative 11 times, it's negative 2 raised to a power, so I'm going to want to put that negative 2 in parentheses, to the n minus 1, where n is greater than or equal to 1. And again, if you can pick the common ratio right out of the sequence, then by all means go for it. But if that's something that you think you're going to struggle with, then get comfortable doing this computation where you take two consecutive values and divide them. So here, negative 3 and 6. The one further down the sequence is the one that goes on top. So negative 1/2 would be my common ratio. So a sub n would be equal to 6 times negative 1/2 times to the n minus 1, n greater than or equal to 1. It's a lot of writing to account for just two terms. So that part makes it somewhat tedious, but it is pretty useful stuff. All right. For this one, I think it's pretty easy to see. R is going to be equal to 3. We're multiplying by 3 every step of the way. So a sub n is equal to 2 times 3 to the n minus 1. You'll notice that the only time so far that I've used parentheses would be when I'm incorporating a negative number. I also tend to use parentheses when I'm incorporating a fractional value. All right. It just so happens that the fractional value also happened to be negative, so it didn't seem that way. All right. 135. 135 on the bottom. So negative 45 over 135. That's negative 1/3. So a sub n is equal to 135 times negative 1/3 to the n minus 1, where n is greater than or equal to 1. All right. Oh, dang it. All right. So then we just have to do the recursive stuff. Recursive models, it's structured the same way as the arithmetic. For geometric, we're only looking at a common ratio being multiplied rather than a common difference being added. But we still find the a sub 1, right? Once we do that, we have to know what the rule is that gets you from one term to the next. But the domain is always n greater than or equal to 2. And again, the reason why the rule is n greater than or equal to 2 is because we already know what happens when n is equal to 1. That's the first term. If we're making a definitive statement of what a sub 1 is equal to, that I don't need a rule for that. That's a fact. That's a given. Right? I need a rule for everything that comes after that. All right. So write the first 4 terms of the sequence. Now they give it to us in recursive form. So we could do it rote, the way I demonstrated yesterday. Write our a sub 1, that's equal to 5. Then a sub n, this is the rule that gets you from term to term. If you wanted to do it just by substitution, you could say, all right, I'm going to follow this rule. I'm going to let n equal 2. So a sub 2 would be equal to negative 4 times a sub 2 minus 1. Which is the same as saying a sub 2 is equal to negative 4 times a sub 1. But since I know that a sub 1 is equal to 5, I would get negative 4 times 5, which is negative 20. All right, so that would be my a sub 2 value. But you'd have to ask yourself, couldn't we have just multiplied the 5 by the negative 4? And I mentioned this yesterday. You'd have to do this if they say justify your work by using the appropriate notation. Justify your answer, sorry, by showing all work using appropriate notation. So prepare for the worst and hope for the best. All right. So if I needed the third term of the sequence, I got the first two, I could follow the same process. Let n equal 3. A sub 3 would be equal to negative 4a to the 3 minus 1, which is negative 4a sub 2. Since a sub 2 is now known to be negative 20, I can make that substitution. Negative 4, oops, forgot the negative, times negative 20. That gives me a clean 80. So a sub 3 would be equal to 80. That would be the third term of the sequence. And you'll see that we could have gotten that by taking the negative 20 and multiplying it by negative 4. All right, and then we would just need to do that for one more term. Let n equal 4. A sub 4, negative 4, a to the 4 or a sub 4 minus 1. So a sub 4 is equal to negative 4 times a sub 3. A sub 3 is now known to be 80. So negative 320 is what we would get for a sub 4. All right. But again, a recursive formula tells you how you get from one term to the next in the sequence. So all this is saying is that you have a common ratio of negative 4. So if I want to get from one term to the next in the sequence, I would multiply every term, or any term, by negative 4, and that would do it. All right. So multiple choice question where they say, what are the first 4 terms of the sequence? Boom, done. But if they say show all work and justify with appropriate notation, etc., then you'd have to do this. All right. But writing the recursive formula, that's much easier because again, all you need is the first term and the common ratio. So the R value here, now it may not be obvious at 81 and 27. It may be more obvious if you look down the line, you see 9 and 3. You'd say, what do I got to do to get from a 9 to a 3? Well, I would divide by 3. But we're multiplying. So I wouldn't say divide by 3, I would say multiply by 1/3. So you can write the fraction off on the side if you want, or you could just kind of reason it out. But either way, you have our first, or we have our first value of 81. We have our rule. We're going to take our common ratio and multiply it by the term that comes before the nth term. And only apply that rule for n values greater than or equal to 2. But like I said, like sometimes you look at it and you think you know it, but maybe you're not sure. If you recognize that anytime you see an alternating sequence, the R value has to be negative, then you could almost disregard the negatives and say, okay, how do I get from a 9 to an 18? R would have to be equal to 3. But you'd say, oh, but it's alternating, so let's make it a negative 3. Worst case scenario, though, take that negative 18. Oh, I'm sorry, 2. Take that negative 18, divide it by 9, and you'll get that negative 2. No matter how many times I looked at that 9, I kept seeing a 6. So anyway, you got an R value of negative 2. We know the initial value, so a sub 1 is 9. A sub n, well, I'm going to take the previous term, the term prior to the nth term, and multiply it by negative 2. So negative 2 times a sub n minus 1, where n has to be greater than or equal to 2. All right. And we have some other follow-up questions here before we get to the assignment. But the follow-up questions really, first 4 terms of the sequence, I'm not going to do it using this approach because it takes too long. what I'm going to do is I'm going to look at this and say there's a common ratio, an R value of 3. All right, I'm starting off with 2. I'm multiplying it by 3, the next term of the sequence. 2 times 3 is 6, times 3 is 18, times 3 is 54. They want the value of C. They defined it as C instead of A. So when they say find C4 minus C2, they're saying fourth term, second term. C sub 4 is equal to 54. C sub 2 is equal to 6. C sub 4 minus C sub 2, 54 minus 6, 48. Now here they use some function notation. They said b of 1 is equal to 3. That notation, just going back to the top here, that's an alternate form of notation, but it amounts to the same thing. All right, so when I see b of 1, I can also write that as b sub 1. So it means b sub 1 is equal to 3. And this also means b sub n is equal to 2 times b sub n minus 1. All right, so my first move here is to translate whatever they're asking in the form that they're asking it into a way that I'm more comfortable with. So for example, this one is saying b sub 2, b sub 3, b sub 4. And eventually they're going to ask us for b sub 15. All right, so they gave us the recursive definition, but that's great because that's easy to work with. All right, we don't have to make any substitutions. They gave us the common ratio. That common ratio is 2. We're starting off with 3, multiplying by 2, 6, 2 again, 12, 24. They're only asking us to go out to the fourth term. This is b sub 1. Now we have b sub 2, b sub 3, and b sub 4. So we have everything we need. But they are asking us for the explicit rule. All right? So that's pretty easy too, because we have the initial value and we also have the common ratio. So they're using b's instead of a's, so we'll stick with that. So b sub n is equal to the initial value, 3, times 2 to the n minus 1, where n is greater than or equal to 1. All right, that's where the big bit of studying is going to come into play, is recognizing the difference in formulas between recursive and explicit. All right, knowing when to use which. Now they're asking us to find b sub 15. For larger values, it's probably better off to do it using the explicit formula, because I don't have to actually double, keep going down the line here until I get to the 15th term, although I could do that. What I could just do here is find b sub 15 by either replacing the 15 or the n with a 15 in the formula, or I could put the formula in the calculator under y equals, just like we did before, 3 times 2 raised to the n minus 1, so x minus 1. All right, so 3 times 2 to the x minus 1. Go to the table. Make sure that the values are correct. 3, 6, 12, 24, those are the first 4 values that we came up with. Then slide on down to the 15th value. And we have this number here, 49,152. So much more straightforward to do the computation when you're dealing with the explicit model than it is necessarily when you're dealing with the recursive. All right. So that's it for the unit. You do have an assignment. That's going to be the next page. But you could ignore the review questions, because that's what you would have done if you were to take a test on this. But only page 35. I'll get the submission area up. It'll be also due. All right. So that's the trade-off. You get assignments and you get a quiz, but you don't have to take a big test. All right.